Hello, everyone. In this video, we are going to look at Huffman codes. Huffman codes are prefix codes. Okay, so let me first explain what a prefix code is. So in coding systems, so we have the map characters to binary coding. So for binary code, so this is a encoding. And then the other direction is when you read a binary code, you can return back to its to the characters to the character it represents. So this other direction is called decoding. Okay, so and then we have two kinds of coding systems. So one is fixed length code. So there's a fixed length. And the other is a variable length. So variable length code. And Huffman codes are variable length codes. Okay, so now let's see for fixed length code, how it works. So for the fixed length code, for instance, using 8-bit coding, 8-bit fixed length code, we know that for English, we use the ASCII code, so that is 8-bit fixed length code. So this ASCII code. So it is like this. So so you get, if you think about this is a tree, and each edge is going to be either 0 or 1 or 0 or 1, right? So then a fixed length code is just like a tree. And for each pass, you have 8 edges. Okay, and then you got maybe 1, 2, and then 9, and then A, B, and also the capital. So this is or is you got 2 to the A at this level. So this is the fixed length code. So encoding is easy, and decoding is also easy because you read 8 bits at a time, and then you look at the mapping table, then you know which character it represents. Okay, now for the variable lengths. For variable lengths code, so for variable length code, we so our encoding part, you can obviously you can just for any character, you can just say, okay, I'm going to use a particular binary code to represent it. So the encoding part, it's arbitrary, but you want to make sure that when you do decoding, there is no ambiguity. So in order to satisfy this, we want prefix code. So what prefix code? What prefix code means is No, so this means that no code is a prefix of another code. So this is a condition that guarantees decoding. So decoding is unique. So to understand this, maybe we can just use a simple example. For instance, let's say I uncode A to 001, then I uncode B to, let's say, 0010. So encoding part, it's sort of arbitrary, but then when you want to decode, then there is an issue. For instance, when you do the other direction, let's say when I see this 001, and if I use this, then I know that this will be represent A, but if you read one more zero, then you will represent B. So I have no idea, since this is a variable code, it's not fixed length, I don't know when I will start reading. Assuming to have, just to make so I can say that I have, just want to make sure. So let's say I have 0010, and then I have, I read. So this is the encoding part, as I said, is arbitrary. So let's say I have this binary string, and then you may have some others. So then I read this, and then I read 001. Do I know this is A or not? Since it's a variable length, so then I would either keep on going, and then I would say, oh, this is 0010. Is this a B? So is this portion B, or we use this portion? To solve this problem, we use prefix code. So this part is not a prefix code because A is a prefix of B. And we need to make sure none of the code is a prefix of another. And then when we want to do the decoding, so we will just read from left to right. The first one, the first binary string that maps to a character, then we will simply use that character because it's not going to be, so this portion is not going to be a legal code of another character. Okay, so that is the concept of prefix code. All right, so now let me go back to the slides. We just explained what a prefix code is. So Huffman codes are prefix codes. So first of all, and second, Huffman code gives us the minimal cost. So in the sense that, so first of all, prefix code, how do we come up with a prefix code? So prefix code is determined by so this is dynamically determined by the input file. And so we want the uncoded. So let's say you have an input file. Let's say this input file contains 1,000 characters. And using fixed length code, let's say 8-bit fixed length code, you would need 8,000 binary bits. So your binary string is this long. So this is binary strings using fixed length code. Fixed lengths. Now using variable lengths, and I don't know, right? So I don't know, but I want this, the binary string as short as possible. When I convert this f to binary string, I want that binary string to be the shortest possible. And Huffman code is a method that provides a shortest binary representation of any input file. So for dynamically, so you have an input file, then I will come up with a variable length code to represent f, so that the binary string for that f is the shortest, has the shortest length. So now to get this into an example, so let's say I have a input file. And just for the sake of argument, so we assume this f consists of only 6 letters or characters, A, B, C, D, E, and F. Okay, and let's say the frequencies, well, this is in thousands, or it really doesn't matter, just frequency. The unit doesn't matter as long as they are uniform across the, it's the same across all characters. So let's say in this particular example, A appears 45 times, B appears 13 times, C 12, D 16, and E 9, and F and 5. Since we have only 6 characters, so you can dynamically determine a fixed length code. So we only need 3 binary bit to represent one code. Or if you use ASCII, and it's 8 bit. So let's say we have fixed length code, so code word, right? So then this is the, so if you use 3, so you add this up. So 45 plus 13 plus 12 plus 16 plus 9 plus 5 and so on. You add them up and they multiply by 3. And that would be the fixed length code string. If you use ASCII and then you add them up and multiply by 8. So right now, using this, multiply the total. So we can just add them up. Let's say 45 plus 5 is a 50, right? So this is 50. And this is 25. And this is also 25. So that's 100. So using prefix length code, using fixed length code, if you use ASCII, that would be 800. And using the binary strings, 800 bits, and using fixed length code word just for this 6 characters, it will be multiplied by 3, so that will be 300. But if you use variable length code word, for instance, it is a variable fixed length code. None of the code is a prefix of another one. And so then you can just calculate how long this binary string will be. So 45, so this is 45 plus, okay, so this is 300. And here we're seeing how long it's going to be. So 13 plus 12 plus 16, that is 41, isn't it? This time times 3. And we have variable length, so this is 4. So we have how many? So this is 9 plus 5 plus 14 times 4. So what's going to be? So this is going to be 45 plus 1, 2, 3. plus 56. And obviously, this is less than 300, right? So you can figure that one out. So this is 5. I'm sorry, this is a 168 plus this. So this is going to be 4, 2, 2. So this is less than 300. So this is a better. It saves, so your actual storage will be smaller to say this uncoded file. So now how do we construct half-length code? So as we saw earlier, so we can look at this code words. Each code word starts from the root and to a binary, so converted to a binary string. So it will be some of the, for instance, the most frequent character should just have a very short code, and then the next frequent maybe a little longer, right? So in other words, we are thinking about a binary tree. So this is going to be starts from 0 and 1, and then 0, 0, 1. So some of them longer, some of them shorter. So that only the leaf level will be your code. So this is leaf. So we can view any prefix code system as a binary tree like this. So that makes sure that none of the code is a prefix of the other using this binary tree. Earlier, when you have a fixed length code, it is not a binary tree, right? So it depending how many code you have. So this is, they all have the fixed length. That's not binary tree. So it is a binary tree that provides us a prefix code. And then we can look at the cost. Okay, so we can turn the frequency as a weight, right? So this is represents frequencies. Okay, frequency. And we think about that as a weight. So we want the cost that will sum up, for instance, we want, let's say I have this node and I have, what is a weight 1 and weight 2. And then I want to have, you sum them up. So I want the total cost. So this will be W1 plus W2. So you move up to the root. I want the total cost to be as small as possible. The reason is that I will consider this length, right? So the length would be, so what I want is, I want, so let's say this is length. This is another length, right? So the length multiply the frequency here, the length multiply this, depending on this tree, we add that up. I want that to be as small as possible. So then we can, so after we understand, we have this understanding, then we can use a very straightforward greedy algorithm to construct a prefix code as follows. This is example that we have. So we have, remember, we have A, B, C, D, E, F. A is 45, so this is its weights, and B is 12, and B is 13, 12, C is 12, D is 16, and E is 9, and F is 5. So this is a greedy algorithm. We look for the two, because we want to construct a binary tree to represent these characters with the weight. So we want to find the two characters with the smallest weight. So this will be this. So we add them up first. So this is E. So this is E and F, right? So this is E and F. So we add them up. So we can say on the left is always 0, the left child. So this edge is always 0. The right one at the right edge is 1. And then we add this up. So the total weight now becomes a 14. So what we're going to replace the EF is now we replace with a new symbol. So let's say I replace it with a new symbol, and I'm going to call this, let's say I use EF with a bracket to indicate this is a new symbol, and this new symbol has 14. So we look at this 14 and replace this. All right, so it goes into this place. Then we repeat the same strategy. We look for the two symbols with the smallest weight. So in this case, it's these two. So B and C, so we add B and C. C is smaller, so we put it here. So it's the left. B is 13, we get 25. So this is, I'm going to call this EF. I'm going to call this BC. So I'm going to replace this with a new symbol BC, and this is 25. Okay, so now we repeat the same algorithm. So this time B and EF, a new symbol with a bracket EF. So this is 30. So we merge them. So these two now merge them. So we get a new symbol. Let's call it DEF. So this time is 30. So this is gone. So what I left is A, B, C. No, this is still bracket. So we got three symbols left. So this time these two are the smallest. So we merge them. So we merge these two. So this is DEF. So merge these two. So we got B, C, D, E, F. And this, after we merge this, we got a new symbol. So this is B, C, D, E, F. And that is, the new weight is 55. And then now we only have this two left. So this is gone. And then we have these two left. How finally we merge them. And that is how we construct this prefix code. And this algorithm is called, this algorithm was first designed by Huffman, and hence we call it Huffman tree. Using this greedy strategy to build a prefix code, that prefix code tree is called a Huffman tree. Okay. So next, we need to show that this greedy choice works. So as we know, that does it really provide us with a minimum code and the greedy choice. So this is a correctness proof of the greedy choice or of Huffman's algorithm. So what we need to show here is, suppose that this is an example from your textbook. Okay. So that X and Y have the smallest frequencies. Okay. So according to our greedy choice, so we need to merge X and Y first. So at least we want to, because they have the smallest frequencies, and we would merge X and Y first. So this is X. This is Y. We're going to merge them. And suppose I have a minimum prefix code tree, and X and Y are not merged first. So let's say in this particular example, assume, right? So there may be other situations. So this is Y and this X. So what I can do here is I will say that so this is a minimum. So what I need to do is that if I change it, so for instance, I'm going to move this X down here. And so in this tree, this is called T prime, so we can compute its total cost. So now, as you can see here, so for this A, now A, the frequency is at least as big as X. So for this tree, so the cost, so this cost is smaller or equal to, right? So it's not going to be greater than, because it's the frequency of, so X is smaller than A. So if you swap this, we don't change the other one. So we know this tree has the cost of this tree is at most the cost of the minimum. Okay. And likewise, after that, I'm going to swap Y and B. Now again, Y is the second, Y and X and Y are the two smallest. So again, the cost is greater than or equal to this, but this is already minimum, right? So this has to be minimum. So this has to be minimum cost. So this means that our greedy choice works. So you can always do this. However, of course, using this algorithm, our variable length code may not be unique, depending on whether you put X on the left first or X on the right first. And so in this particular case, if this is a minimum, then this A and B will also the two nodes with the smallest frequencies. So then, of course, that means that you will not have the unique prefix code. So that means that when we actually, let me go to the whiteboard again. So when we produce, so let's say this is a file. When we encode it into a binary. Right? So we will have to you have to go with the mapping, the Huffman tree mapping. So the table we saw, right? So this is the code table. So which means a table like this. So it's a character 1, character 2. Let's say this file contains character, okay, and then there's a code, there's a code, there's a code. So you have to attach that code. So when you do decoding, and so when you do decoding, so you have the compare. So when you read, so you read a binary, and then you want to go back to this direction. So then you check the a string matching, right? So which string it matches on this table, and that will be the unique character you will get back. Okay, so this is the end of this video. Thank you for watching.